This is part 1 of the lectures on Chapter 2, Protecting the Ozone Layer in Chemistry and Context, 7th edition. For this first part, we'll be looking at what is the ozone layer and where is it. We'll also take a look at atomic structure in order to understand the chemistry of ozone a little better. It will involve taking a look at subatomic particles, what makes up the atom, how we identify different atoms by their atomic number, as well as different isotopes perhaps by their mass number. We'll also look a little bit at valence electrons and what those are. And we'll be looking at the Lewis model for drawing structures of molecules. That will involve something called the octet rule, and we'll see when to put multiple bonds between atoms. Sometimes there's a single or a double or a triple bond between atoms. And we'll also talk about this concept called resonance, where we sometimes need to include more than one structure to illustrate the true nature of a molecule. So some of the questions for this chapter are, what would happen to us if the ozone layer continued to thin, if we did not take action to stop the existence of the ozone hole? And down here, this picture is showing just 3 red atoms side by side, which is the representation for the ozone molecule. What does the ozone layer do? And how can we protect it? And what chemicals are causing the ozone depletion today? So the first video is titled The Ozone Layer.
Ozone is an atmospheric gas concentrated at an altitude of between 20 and 30 kilometers. It forms an envelope around Earth known as the ozone layer. Ozone is a blue-colored gas whose molecules are composed of 3 oxygen atoms. The ozone layer acts as a shield against the sun's ultraviolet rays. This is because ozone molecules can absorb the ultraviolet rays. They then decompose into 1 oxygen molecule and 1 atom of free oxygen. This molecule may react with another ozone molecule and form 2 oxygen molecules. In its turn, an oxygen molecule may absorb an ultraviolet ray. It thus liberates 2 oxygen atoms, each of which may regenerate an ozone molecule. The destruction and regeneration reactions of ozone balance out naturally. However, certain atmospheric pollutants encourage destruction of ozone molecules. Because of this pollution, the ozone layer is thinning and protecting us less effectively against the sun's ultraviolet rays.
Okay, so let's talk about what the video described. Ozone is a molecule made of 3 oxygen atoms. Ozone can be broken down when light strikes the molecule, and therefore, instead of the light going all the way to the Earth, the ozone layer blocks some of that light. Ultraviolet light is harmful to organisms. We need a certain amount of light on Earth, but if we have too much of certain types of light, ultraviolet light, it can be very damaging. So this shielding of certain types of light protects us. So that ozone layer is critical. The ozone layer is within the stratosphere. This picture here is showing that, okay, 0 to 10 kilometers is the troposphere. Then from 10 to 50 kilometers, we call that layer of the atmosphere the stratosphere. In the bottom part of the stratosphere, we have the ozone layer. Now, if we were to fly from the troposphere into the stratosphere, we would not look down and see a band of ozone. It's not visible with the human eye, first of all, but also it's not such a specific banding. It's more of the most concentrated region of ozone in the atmosphere. So here on the x-axis, we have increasing concentration to the right. On the y-axis, we have altitude. You can see at 0, close to ground level, there's some increase in ozone from pollution, as we talked about in Chapter 1. And then when you get into the stratosphere, you see this very large peak of ozone concentration. And it's where the largest or the most concentrated regions of ozone are that we define as the ozone layer. Now, ozone is formed from the absorption of light by oxygen molecules. We talked about earlier, it also breaks down in light. So it's a reversible process in a way. Ozone is what is called an allotropic form of oxygen. What does that mean? Well, that means that oxygen, the atom itself, can form a number of different molecules with only oxygen in that molecule. Okay, so we have O2, we have O3. These are different allotropes of oxygen. Since they have different numbers of atoms of oxygen and different structures, they have different properties. So another example would be carbon. We all are familiar with the different allotropes of carbon, but perhaps just not the word allotrope. Graphite that you find in your pencil lead is one form of carbon. Diamond is another. The differences between those two substances are how the carbon atoms are connected, but they're still pure carbon. So we talked about ozone in the troposphere. In the troposphere, it's a pollutant. Ozone contributes to smog and other types of pollution. In the stratosphere, it's important. We need ozone in the stratosphere. If we take away that precious ozone, stratospheric ozone layer, that's going to increase the amount of dangerous, high-energy ultraviolet light that reaches the Earth. So here's a Thinker Buddy question. Which statement concerning ozone is correct? Ozone is considered A, beneficial in the troposphere because it protects us from ultraviolet light, but it is an air pollutant in the stratosphere. B, an air pollutant in the troposphere, but beneficial in the stratosphere because it protects us from ultraviolet light. Or C, an air pollutant in both the troposphere and stratosphere because of its toxicity. Or D, beneficial in both the troposphere and stratosphere because it protects us from ultraviolet light. B is correct. It's an air pollutant in the troposphere, close to ground level. It can be a lung irritant. It's a pollutant. But in the stratosphere, it will absorb dangerous ultraviolet light. So now we're going to watch a little overview of the structure and size of the atom. What are the three major parts of the atom? From the video, Hopefully you saw that the three major subatomic particles were the proton, the neutron, and the electron. Now another Thinker Buddy question. What is the charge and location of all three particles? Well, neutrons have no charge, and they're in the nucleus next to the protons that have a +1 charge, also in the nucleus. The electrons are outside of the nucleus or surrounding, very far away from the nucleus, and they have a -1 charge. So this table summarizes that. The relative charge, we say relative because really if you want to use the units used by physicists, then the number doesn't look so pretty. So we just translate it into a relative charge. Protons and electrons have a similar charge and they're opposite in sign. Relative mass, we've done something similar with mass, as we've said the proton has a relative mass of 1, neutron 1, and then the electron is about 1/2000th of a degree smaller than the proton and neutron. So relatively it hardly contributes any mass to the atom itself. Now another key point is that the number of protons is what defines an element. If you have two atoms and they have different numbers of protons, they must be different elements. Each element is defined by the number of protons. So isotopes, what are isotopes? They are different forms of the same element. So if we're talking about one element, we're talking about atoms with the same number of protons. But what can vary is the number of neutrons. And since neutrons have a relative mass of 1, they will change the total mass of the atom. So here we have an isotopic symbol. It involves the element symbol, in this case carbon, so C. And then carbon, if we're talking about carbon, it's always 6 protons. Anything with 6 protons is carbon, and anytime you have a carbon atom, it has 6 protons. These two numbers, this number and this atomic symbol, are linked. Now what can vary is the mass number. This is the total number of protons plus neutrons. And that's usually abbreviated with the letter A, atomic mass, and then the atomic number is Z. I like to remember it, the atomic mass, A, and Z, atomic number. The atomic number is important in determining the identity of the element. So it can also be written to distinguish between the different isotopes of carbon. We put the 12 after the written word carbon to indicate, okay, it's the isotope with 6 protons, 6 neutrons for a total mass of 12. On the periodic table, it gives the number of protons, or Z atomic number, and that's frequently located above the element. So again, on the periodic table, they don't necessarily have the atoms arranged in any way that looks like our isotopic notation. They have the atomic number on top of the element, and then they have the weighted mass number below. Again, the atomic number is the number of protons. That will tell us something about nuclear charge, right? If each proton has a +1 charge, then oxygen would have a nuclear charge of +8. This weighted mass number is an average of the masses of the different isotopes. And I'll talk about more what that means right now, actually. Let's look at carbon. So carbon-12, it has 6 protons. Carbon-13, well, we're talking about carbon, so it also has 6 protons. Carbon-14, well, we're talking about carbon still, so it still must have 6 protons. But look what differs between the isotopes. It's the mass number, A, and the number of neutrons. You see that the number of neutrons varies. These percentages here are giving us the relative abundance of that isotope on Earth. So carbon-12 is clearly the most predominant form of carbon. But there's a little carbon-13. And there's a little bit of carbon-14. So if you happen to pick up a handful of carbon, it would have these ratios of isotopes. And so when they put that mass on the periodic table, what they're doing is they're saying, okay, 98% or 99% have a mass of 12, but a little bit has a mass of 13, and a little bit has a mass of 14. So they take an average, multiplying the mass by the fraction, plus the mass times the fraction, plus the mass times the fraction. And that gives this what is called a weighted atomic mass on the periodic table. So when you're talking about a neutral isotope without charge, the number of protons will equal the number of electrons. So carbon-12, there's no charge associated with this here. So it has 6 protons in the nucleus. We would assume it has 6 electrons. If you wanted to look at an example of a charged isotope, it would have to have a plus or a minus number, or a +2 or a -2, along with the isotopic notation. So sodium, since it has a +1, it must have one more proton than electron. So the charge on the atom is going to be the number of protons minus the number of electrons. In the case of sodium, sodium has, if we look at the periodic table, sodium has 11 protons. Okay, if it has 11 protons and a charge of +1, it must only have 10 electrons for this particular form of sodium. Let's do a thinker buddy. How many protons, neutrons, and electrons are in a neutral atom of chromium-52? Notice how I'm just indicating the mass number of chromium by putting it after the name, chromium-52. Why don't I need to include the atomic number? Because every time I have chromium, I always have 24 protons. So just by stating chromium, a person can look at the periodic table and see the atomic number. I don't have to include both the atomic number and the element, even though we do when we write the formal isotopic notation. So how many protons and neutrons and electrons are in a neutral atom of chromium-52? Do we have 24 protons, 24 neutrons, and 24 electrons? A. Or B, 24 protons, 28 neutrons, and 24 electrons? Or C, 24 protons, 28 neutrons, and 28 electrons? Or D, 28 protons, 52 neutrons, and 24 electrons? So B is correct. So remember that atomic number, Z atomic number, tells us the number of protons. Now, the number of electrons, we're looking for a charge. There's no charge here associated with this isotopic symbol. If that's the case, then we also have 24 electrons, because in a neutral isotope with no charge, the number of protons equals the number of electrons. How do we get the number of neutrons? Well, we know this mass number is the number of protons plus the number of neutrons. So if we know the number of protons, we can do the number of neutrons must equal 52 minus 24. So when we do that, we come up with 28. Another thinker buddy. Elemental oxygen, oxygen gas, and ozone, all forms of oxygen, are examples of A. Catalysts, B. Isotopes, C. Structural isomers, or D. Allotropes. This is what we talked about earlier, defining that term allotrope. And we talked about how carbon, when it's bonded differently in graphite versus diamond, those are also allotropes of carbon. Different structures and formulas, number of atoms for one particular element. So now there are 2 mini lectures on Lewis structures. You may want to write down information to include in your study note cards. Okay, so now let's do a Thinker Buddy question using the steps outlined in the Lewis structure lectures. Okay, you're back. Let's go through the solution for this problem. So step 1, count the total number of valence electrons. Well, we learned that the number of valence electrons on an element is the same as the group number. So oxygen is in group 6, so it has 6 valence electrons. Okay, 6 valence electrons, but there are 3 oxygen atoms. So we have a total of 18. Okay? Place one bond for each to connect them. All right, so oxygen, oxygen, oxygen. Distribute extra electrons on the outside atoms in pairs to fulfill the octet rule. Okay, so I'm going to start doing the octet rule on these. I'm going to draw little circles so it's easier to see. Okay, so now that's got 2 from the single bond, 4, 6, 8. That's my octet rule there. 1, 2, 3, 4, 5, 6, 7, 8. Remember that each line represents 2 electrons. So I've got an octet on these 2 oxygens, so they're happy. Place extra electrons on the central atom. Well, how many have I used so far? I've got 2, 4, 6, 8, 10, 12, 14, 16. I've used 16 electrons. So I put my remaining 2 on that oxygen. But what's wrong? Something's not quite right with this picture. If you got this far, that's pretty good. But we need to do one more step. Yes, that's right. Or maybe you didn't get it, but that's okay. This oxygen atom only has 2, 4, 6 electrons surrounding it. So we need to redistribute the electrons by making double or triple bonds. So they can come from either side, but what we need to do is put some of these electrons and form a double bond between either these 2 atoms or these 2 atoms. So the final structure would look something like this. And it doesn't matter where you take those electrons from, if you used these, or you used those, or these, or those, or those. As long as you got a double bond for one of the two sides of the ozone molecule. So this, your final answer should look something like this. Now, the biggest problem people have with Lewis structures is they like to skip steps. You're going to run into trouble if you skip steps. You should connect all the atoms first, then distribute the electrons on the outside atoms. Then if there are extra ones, place them on the central atom. Then you make double or triple bonds. People like to somehow jump to step 5 after doing step 1 or skip step 1, and it becomes very difficult at that point. Now let's talk about what are called resonance structures. So as you saw with ozone, there were almost two possible answers. We could have put that double bond on the right side or put that double bond on the left side. So which is the correct structure? Is it the one with the double bond on the left or the one with the double bond on the right? Well, in reality, these are resonance structures or resonance forms or resonance hybrids. These two structures, neither are really the true structure of ozone. But drawing out both of these possible structures with this double-sided arrow gives all the resonance forms of ozone. So, again, what that means is essentially if you can have electrons move around the molecule to have a double or triple bond in different locations, then those are different resonance forms of a molecule. And because of these resonance forms, the actual molecule doesn't really have single and double bonds. It's really a hybrid of the two. And the actual ozone molecule can be seen almost as having two single bonds and a half. This bond is somewhere between a single and a double bond. This bond is somewhere between a single and double bond. It's as if you almost took the electrons and spread them out over the entire molecule. So a good indication of whether or not you have resonance structures is just what happened to us with ozone. Where do I take the electrons to make the double bond? Oh, I can take them from here and make that double bond there. Or I could take them from here and make a double bond there. If you run into that situation, then you are going to have more than one structure for a particular molecule. And let me give you another analogy here. Here we have a unicorn, which doesn't really exist, and a dragon, which doesn't really exist. But when you look at their resonance forms, and the actual animal that exists is the rhinoceros, which is a hybrid of the two. So this, for example, would be, the unicorn would be like one of our ozone Lewis structures. This form of ozone doesn't really exist. Ozone, when we look at it and measure the bonds, they're all identical. When we look at the strength of the bonds, they're all identical. So this form of ozone doesn't exist either. What does exist is this hybrid between the two, with those electrons spread out between the oxygen atoms. You won't have to draw anything like this. Okay, what you may be asked to do is, well, understand this concept of multiple Lewis structures giving us an idea of the actual structure, so the idea of resonance, and then you may be asked to just draw these different types of Lewis structures contributing to the resonance hybrid. But you won't have to actually draw the hybrid structure. So let's do another Thinker Buddy question. How many non-bonded electron pairs are there on the oxygen atom in the Lewis structure for carbon monoxide gas? 4A, 3B, or 2C, 1D. How many non-bonded electron pairs are there? So to solve this problem, we need to draw the Lewis structure for carbon monoxide. So let's go through the steps. Step 1, what group is carbon in? Carbon is in group 4. Okay, so it has 4 valence electrons. Oxygen is in group 6. Okay, so we have a total of 10 valence electrons. Remember, we don't want to skip any steps. Connecting them is easy, just one bond between the two. Then we want to start giving octets. 1, 2, 3, 4, 5, 6. How many electrons we've used? Up of our 10, we've used 2 for the bond. 4, 6, 8 to give oxygen the octet. That means we only have 2 left for the carbon, but that's a problem because carbon then only has 4 electrons around it when it needs an octet of 8. So in order to give it the other 4 electrons it's missing, we need to take 2 sets of lone pairs from the oxygen atom and make a triple bond. Okay, so this is the final structure of carbon monoxide, and the question has us count how many non-bonded electron pairs are there on the oxygen atom. On the oxygen atom, well, there's only 1. So D is correct. This ends Chapter 2, Part 1. And you may want to take a break or read through the corresponding text sections. Or, you may want to read through the text and then watch the lecture videos, whatever works for you.